Okay, so let's get ready to get going. I think I'll just toss up our term schedule again, just to show where we are so far. So here's today, the 6th of October. We're 2 weeks out from our first term test. I'll put all this up on Brightspace, but we're gonna write our term test, not in this classroom, but out in the big lab. So if you did physics 1020, 1050, or 1021 with us, this would have been your physics lab. It's room 2038, so right next door to your current lab. We're gonna write it there just because there's a little more space and we'll be a little bit more comfortable, so I will post that. As you start to get ready for the test, you know, sometimes people ask what they should study. I recommend you start with the lecture notes. The reason I put stuff in the lectures is because it's the stuff that's important for you to take away from this course. So the lectures are probably your first point to start studying. Almost every class there are homework problems. It's good to be able to go through those. Then also your assignments and the problem session questions. Those are all good practice for the test. And I don't remember if I've got it open or still hidden, but there should be some stuff under midterm 1 on your Brightspace. I'll check when I go back to my office today to make sure that's open for you. And like I said, I don't know, a few classes ago, you can bring a sheet of notes into the test with you, write whatever you want on it. It just has to be an 8.5 by 11, single-sided in your own handwriting. So that's the only restriction. I think that's all I have to mention before we get started for today. Does anybody have any questions? So last day we talked more about electric fields. We said that we can have continuous charge distributions. They have electric fields around them. We looked at the electric field of a charged plane. We used the idea of a surface charge density sigma. We put two planes together and we got a capacitor, and we found the electric field around a capacitor. We're going to start today with another capacitor example. So in the example we'll start with today, we have an electron gun that creates a beam of electrons. They're moving with 0.1 c. C means the speed of light. That's 3 times 10 to the 8 meters per second. Moving through a parallel plate capacitor with a field strength. So this is the electric field E, 50,000 newtons per coulomb. By how much does the beam deflect as it passes through the capacitor? Okay, so by how much does the beam deflect as it passes through? So it's moving through. So let's see some things that we know. The initial speed is 0.1 c, so 0.1 times 3 times 10 to the 8 meters per second. So our initial velocity. This question is not really specific about the velocity. If this were a test, I'd probably be more clear or even put it in the picture. We've got our beam of electrons coming in at the bottom near the negative plate, and they're initially coming in horizontally. So there's our initial velocity. Put that in the picture. Put on the coordinate system x and y. So our initial velocity is 3 times 10 to the 7 meters per second to the right, or I. So there's our initial velocity, all in the x direction. It's passing through the capacitor, so it starts here and goes to here. So overall, in the horizontal direction, it travels 2 centimeters, so it goes between the two plates. So delta x equals 2 centimeters. By how much does it deflect? It's asking how far does it move in the y direction. Okay, so this is the question before us. We're trying to think of the motion of these electrons. So we need to ask what's happening to them. What are the forces? What are the acceleration? What's the path going to look like as we try and think about this? So we're going to need to talk about the force in order to figure out the motion. So what is the motion? We need the force. So how do we find the force on an electron, on a charged particle in an electric field? We know that the electric force is the charge of our particle, so the charge on the electron, times the electric field. So minus 1.6 times 10 to the minus 19 coulombs. Our electric field, we see it points downwards. It has a strength of 50,000 newtons per coulomb. And it points down, so that's the negative y direction, or negative j hat. So we'll put this through the calculator, and we're going to see that the force on each of those electrons, negative times negative gives us a positive, and then it's 8 times 10 to the minus 15 newtons j hat. I wrote out my equation as a vector equation. It's fine if you want to do it that way. You could also think my electric field is down, my charge is negative, so I know my force has to be up. If you prefer to reason it that way, that's fine. It's right either way. So if we think about the force, that points straight up, so there's the force on the electron. The force is up, the initial velocity is to the right. There's no force in the x direction, so it'll keep moving in the x direction. There's a force upward in the y direction, so it will start to drift upwards. So the path of the particle is going to look something like this. Okay, so that's what the motion is going to look like. This motion here, if we turned our picture around, it might become more familiar. So if we have a ball and we throw it to the left, we know it's going to move with projectile motion, it will fall under gravity. This is the same problem, right? We've got a force pulling it down, it's moving to the left, so we know it's going to move left and down with projectile motion, and we'll use kinematics for the analysis. Same deal here, except it's moving right and up. Okay? So we turn the page around, we still get the same motion. Okay, so now we know what's happening. It's traveling to the right, it's deflecting upwards, it's moving with projectile motion. So let's toss in the words projectile motion just to make sure we don't forget. And now let's get to thinking about our analysis. Let's do our standard approach from Physics 1050 or 1020. Let's make a list of our information and let's see what kinematics we can apply to figure out our solution. So we've got our coordinate system. I'm going to put my origin right here at the charged particle where it enters. So I know that my initial x position is 0, my initial y position is 0, starts at the origin. My initial x velocity, v initial x, is equal to 3 times 10 to the 7 meters per second. V initial y is 0, horizontal motion initially. Acceleration in the x is 0 because there are no forces in the x. Acceleration in the y is. Okay, I don't know the acceleration in the y, but I know that I can figure this out because I just found the force. So we'll pause here, we'll figure out that acceleration, and we'll put it in our table. In this problem, if you looked at the electron and you said, shouldn't I include the weight or the gravitational force? Technically that's true, right? Gravity does act on it. If you calculated it, it would be so tiny that it wouldn't compare to this number. It wouldn't even show up in your calculator under calculations. That's why we leave it out. That's why we neglect it. Okay, so let's do our acceleration so we can put that in the table. So sum of the forces in the y direction is mass times acceleration in the y. Acceleration in the y is going to be our electric force divided by the mass. 8 times 10 to the minus 15 newtons divided by mass of an electron, 9.11 times 10 to the minus 31 kilograms. AY is 8.78 times 10 to the plus 15 meters per second squared. Mass of an electron, I don't expect you to remember that number. I do expect you to know that you could look it up in a book. On a test, I would give you the value. So there's our acceleration. Let's put that in our table. We're trying to find where does it end up. So we want our final y position. We know where it ends up in the horizontal. It goes all the way across, 2 centimeters, 0.02 meters. There's all of our information. We don't know how long it travels. Let's put a t equals question mark there because we usually like to find our time. So if we want to find our final y position, let's write down one of our kinematics equation that lets us calculate position and see where that's going to take us. So my kinematics equation that I would like to use to find my final y position is that y final is y initial plus v initial y times t plus 1/2 times ay times t squared. This is probably the kinematics equation that you tend to remember. So my y initial is 0. My v initial y is 0. So these two terms are gone. Y final equals 1/2 times ay times t squared. This equation looks good. It lets me find my y final, except I don't know my t. So to keep going with this equation, I need to figure out my t. I ask, do I know any other information? And I know lots of stuff in the x direction. Let's go to the x direction. Let's find our time. Let's come back to the y equation. Okay, so we'll pause here. We'll come to our x information, and we'll find our time. So x final equals x initial plus v initial x times t plus 1/2 ax t squared. X initial is 0, ax is 0, so we don't have to worry about those two terms. So then our time is our final x position divided by our initial x velocity, 2 centimeters divided by 3 times 10 to the 7 meters per second gives us a very fast time of 6.67 times 10 to the minus 10 seconds. It's very fast, but that makes sense. It's not going very far, and it has a really high speed, so it doesn't take long to get across. We've got our time. We can come back to y and find our position. So now yf equals 1/2 times ay times t squared. 1/2 times 8.78 times 10 to the 15 meters per second squared times 6.67 times 10 to the minus 10 seconds squared. And we get an answer of 1.95 times 10 to the minus 3 meters. If you preferred millimeters, you could say 1.95 millimeters. We can put that in context with our picture, make sure it makes sense. Does it line up with what we said in the first place? So if we start down here and it goes 1.95 millimeters, kind of ends up about here because our plate has got a spacing of 5 millimeters. So we're good here. Yep.
Is it okay if we don't write down the units for each thing that we're plugging in, and we just bring the units to the end if you know how the units are working out?
Oh yes, so the question, if not everybody heard it, is basically, do you have to put the units in every step in the workings? And the answer to that is no. I do it because I think it's a nice habit to show you that all the units do line up. If you leave them out here, as long as you put them in the final step, that is fine. Mostly I think if you struggle with algebra at all, like if you tend to make goofs in algebra and it's easy enough to do, I would say do keep your units in because it'll help keep you in place. If you're really confident with your algebra, then you can go ahead and leave them out. So depends on what you prefer to do. A twist I could put on this question, like there's not tons of ways to change this up. I could ask the question, instead of asking how far does it deflect, I could ask, does it get out through, right? That could be a decent question. In order to figure that out, you would find out how far it would go. If your answer was bigger than 5 millimeters, it would crash in somewhere before. If it was less than 5 millimeters, it would get out. Kind of a different interpretation of the same question. Could change the geometry so it goes up instead of, so kind of we shoot it up vertically instead of horizontally. Not tons of ways to change that one up. Okay, questions? Okay, so it looks like we're good to there. So we'll keep going with electric fields. We're going to come back to point charges just for a little bit. When we talked about our electric fields, what we did previous to now was we said, let's find the electric field at point P. And we drew one arrow at point P and we said the electric field at this point is this much. Now what we'd like to do is get a visualization for the electric field around charges in general. We know that electric fields fill all of space. You know, electric fields are everywhere. Let's get an idea of what those electric fields look like everywhere. So we're going to create what's called a field diagram. This is a term your book really seems to like. I don't know many physicists who actually say this, but your book does tend to say it a lot, a field diagram. More often you would just say electric field lines, and you might toss in the word map. So those are more common terminologies. So we want to see what do the electric field lines look like everywhere. So to do that, let's look at the electric field around this positive charge at a couple of different places and get an idea of what it would look like everywhere. So if I wanted the electric field right here, I would put my pen right here. I would remember that electric fields go away from a positive charge, and I draw an arrow that points away. So that's what my electric field would look like right there. I could draw an electric field right here. I would put my pen right here, and I have to go away from my charge. So that's what it would look like right there. I could draw one over here, and it would go away from my charge. You get the idea? So I could draw the electric field anywhere I wanted to. If I do this everywhere, this is how I get my map of the electric field lines. I basically look at what do all those arrows give me when I look at the arrows everywhere. So this is a map of our electric field. These are the electric field lines. Okay, so those arrows we draw are the electric field lines around this positive charge. So this is showing the electric field lines coming radially out of a positive point charge. A couple of things to notice on this diagram. We know that electric field is KQ over R squared. When we're in close to the charge, that's where our electric field is the biggest. And we see that the lines are closest together there. So your electric field is strong where the field lines are close together or where they're very dense. So close lines go with a strong field. If your field lines are spread out, down here for example, if they're less dense, this is where we get a weak field. Okay, so the density of the lines is proportional to the electric field strength. It gives us the strength. You might notice that these electric field lines don't cross, and that's always going to be true. Electric field lines will never ever cross. And that makes sense. Electric field is a vector. If the two lines crossed, the vector would have two directions at the same time, and that's just not what happens. Vectors can't point two ways at the same time. There is a pretty good simulation. This will work on your phones if you want to check it out. If you Google PHET, P-H-E-T, electric fields, your first hit will be this electric field simulation. I set it up to turn on the grid. It'll just help me know where to put the charges. I'll put in a positive point charge. You see the lines point away from it. So sometimes for an assignment, you might have to draw electric field lines. This simulation can help you visualize those if you want to. Move it over here. I kind of like it right here. The brightness of the lines, I think you can see that a little bit. Where the lines are really bright, that's where the fields are strong. Where the lines are really dim, that's where the field is weak. So strong and close, weak out away. Okay, any questions so far? Yep.
Why the field lines are getting weak when it's extending
Because the electric field is KQ over R squared. If your distance is big, your field is not as strong. Yeah, and on the flip side, when you're in close, your field is quite strong. So that's around our positive point charge. When we did our negative charges, we said that the electric fields go into a negative. So we'll do this for a negative charge. Let's see what those field lines look like. So same idea. If I wanted to know the field right here, I put my pen on this point. I go in towards a negative, might look like this. My electric field right here would go in towards the negative. My electric field right here in towards the negative. So you could draw your field at a bunch of different places in space. Then you draw all of them. They look like this. So into a negative. We get the same idea. The field is strong where it's enclosed, weak where it's far away, and those lines don't ever cross. So there are the electric field lines around a negative. We can do that with our simulation as well. So we can get rid of the positive and we can put in a negative. Same picture except the direction of the arrows just flip. So now everything points in. Same behavior. So that's for a positive point charge and a negative point charge. You might ask what happens if we double the charge. So let's look at that on PhET first, and then we'll draw the picture of it. So if we double the point charge, we know that electric field is KQ over R squared. If we double the charge, we double the field. So let's put in a second charge. We said on the simulation, the brightness goes with the strength of the field. So just watch the brightness of the arrows when I let it go. Right, you see that the field strength increases. So if we double the charge, we change the strength of the electric field. The way we represent that on our diagram is to increase the number of field lines. So if we double the charge, it means we double the field. And when we draw it, it means we double the number of lines. So when I had a single charge, I drew 8 lines coming in. So this is what I had for my single charge. Now with my double charge, I'm going to have 16 lines. So twice as many lines. And then if we think about that behavior of the density of the lines here are denser than the lines here, stronger field here because the lines are denser here. So same behavior still. Okay, questions? No? No, good. So that's positive, negative. That's doubling the charge. Next is what if we put a few charges together? So one system of charges we look at reasonably frequently is called an electric dipole. Your book goes back to this as an example pretty often. An electric dipole is just 2 small charges, equal and opposite, and they're separated by a small distance. So I've got a plus charge and a minus charge. What do the electric field lines look like here? So we're going to apply our rules for electric field lines. Out of positive, into negative, and number of lines proportional to the size of the charge. And then I guess if you were writing a list of rules, you would also say that they don't cross. Okay, so some good things to remember. Let's have a look at this on our simulation, and then we'll draw them. So I'll take out my charges. I'll put in a plus, and I'll put in a minus. So it goes out of the positive and it goes into the negative. Weak far away, stronger in close. So let's draw that on our picture. So we go out of the positive into the negative, and then we have to draw some more lines. They start to curve. Because the charges have the same magnitude, every single line that comes out of the positive has to go into the negative. So it's a pretty common test question that I will ask you. You know, part A is draw the electric field lines, part B is find the electric field at some place, and part C is find the force on an electron at that point. It's a really typical problem to put a few bits of this together. And these are the rules you have to follow when you're drawing this. When you're just doing it for homework, the simulation can help, but you do have to more or less know the rules. Okay, questions here? Yep.
What if like the magnitude of charges are the same? And one was bigger than the other?
I'm so glad you asked. What if the charges don't have equal magnitudes? That's the next slide. Okay? Oh wait, sorry. Just to be silly, I went through that one too fast. So pretty good with the notes. Pretty good on this. So we can have charges with equal magnitudes, and we still have to follow the rules. We come out of a positive into a negative. The number of lines is proportional to the size of the charge. What that means is that for every one line that comes out of this positive, 2 has to come into this negative. So I said out of positive. It can also come out of infinity. And it comes into a negative, or it can go into infinity. So infinity is okay as well. So what that means when we're drawing the picture is I draw one line from plus q to minus q. Okay, so one out, one in. I need another line to go into that q, so that comes from far away. Okay, so now I've got 2 in and 1 out. And then I do that for every line that comes out of plus q. So one goes out and in, I need another to come in. I'll do that here on the bottom. Just try and get one more in there. Sort of hard with big Sharpies. Your book does better pictures than I do. I'm just doing my best. Yep.
I'm just wondering what infinity would mean in terms of electric field. Does it just, the charges just come from space, or?
It sort of means that there are other charges very far away, and that's where they came from. Yeah, so some sort of charge very far away. Yep.
So would it pull like charges from something nearby?
So right here there are electric fields. Other charges nearby would feel forces due to these fields.
Okay.
Yeah, absolutely. So you could say calculate the electric field right here. Then if we put a charge here, it would feel an electric force and it would start to move along those lines. Okay. So that's as many as I'll do in class. I've got a little set of them for you to do for a homework problem. To do those, you can use the PhET simulation if you want to, or if you want to see how well you understand it, you could try and draw them first and then check your answers. And I will post the solutions to them if you want to check them. Okay, so that takes care of our point charges. The other charge we looked at was a capacitor. And we drew those electric field lines, even though we didn't really talk about them that much, like we derived the expression for them. So when we have our plane of charge, the diagram, and I've got that preloaded on a PhET simulation. I'm sure you don't want to watch me putting it. Some people saw me doing it before class. The simulation is kind of neat because when we talked about real versus ideal capacitors, we said it was perfectly straight in the middle and it was 0 outside. what we've got here is an approximation of something that's more realistic, not ideal. So you see you've got all these bendy things on the side, and the field is not exactly zero outside. But in the middle, it does look like it's pretty constant, and it goes from positive to negative. So this one is closer to real than ideal, and we deal with the ideal ones in class. So we go from positive to negative. That's what your electric field lines look like between the capacitor. Any questions there? Okay, and then this segues us into our next chapter, which is all about Gauss's law. We do have one of these Van de Graaffs in the department. I'll bring it in one day when we talk about it in class, maybe when we get to the potential chapter, as long as it's still working. So when we talked about electric fields in the last chapter, we said that continuous charge distributions do make electric fields. You can find those electric fields by doing a calculus treatment, integrating the contributions due to each charge. In some cases, when there's a lot of symmetry, you can use Gauss's law to find the electric fields, and it's a nice, elegant way to find electric fields without grinding through a bunch of calculus. So we're going to take the field lines that we just looked at, we're going to think about some symmetric considerations, and we're going to build ourselves up to Gauss's law. So that's where we're going with this. This is a summary of what we just did. So here are the three sets of charges that we're going to look at. Of course, there are other charges, but we're going to focus in on these. If you have a point charge, it's radially out from the positive, radially into a negative. A plane of charge, it points outwards from positive into a negative. It's constant everywhere and perpendicular. A sphere of charge looks like the point charge in that it's radially outwards. And we'll see that there's some interesting stuff happens inside. Okay, so we're going to come around to looking at all those things. To start our foundation for Gauss's law, we're going to ask what the electric field lines that we know pretty well right now, what do they tell us about charge? Yep.
Are these notes not uploaded yet to the part space?
I put them up yesterday. Yes? No?
They're not up, or not for me at once.
No?
Yeah.
Okay, so then maybe I hid them by mistake.
All right.
Okay. Yeah, and that's not something I can do from my phone.
Yeah.
Okay, so I'll get those visible when I go back. Okay, oh, so it'll all be a surprise. This will be fun. So what we're going to do is take our idea of electric fields and ask, what does it tell us about charge? So I've got a picture here, what's in the box. Apparently I'm supposed to do that with a very pained Brad Pitt voice, but I don't do imitations. So if these are my electric field lines, and this is just a physical model of what's up on the screen, and they're pointing outwards like this and down like this, what's inside my box? There's a positive point charge in there, right? And you know because you can see the electric field lines. So these electric field lines are telling us what's inside this box because we know the field lines around a box. So what's inside this box is a positive spherical charge. So it has to be a positive spherical charge because of the electric field lines. So let's do a couple more boxes. So there's the first one. What if I had a box that looked like this, but instead of having this many arrows pointing out, I had this many arrows pointing out? What's inside this box?
Charge?
Yeah, more positive charge. Okay, so this one is a single plus. This one is two pluses. Okay, so inside this box, why don't we write that down actually? So this one had positive charge. And this one has a bigger positive charge. Okay, let's ask one more question that's probably really easy, and then we'll ask one that will maybe stump you, maybe not. What's inside this box?
Negative charge?
That one's got the negative charge. So we've got the electric field lines pointing in. We know electric field lines go into a negative. So our next box what's inside this box? More than one answer possible.
Nothing is inside this.
Okay, the first answer I heard was nothing. I agree that maybe there's nothing in the box.
A positive and a negative.
A positive and a negative, yep, maybe there's, we just defined that as an electric dipole, so yep, it could be a dipole. Any other ideas? Could be a capacitor, because that would have a positive plate and a negative plate. I sort of had one more on my list. I also thought about a neutron, because a neutron doesn't have any charge, so that could be in there as well, right? What all these things have in common, nothing, a dipole, a capacitor, and a neutron, no net charge. So inside this box, maybe we don't know the details of what's in there, but we know that overall there's no total charge because of the electric field lines, the way they look outside. So this is our basis for getting started. This idea of the box coupled with the electric field lines, the box is a pretty useful thing, and the box is called a Gaussian surface. The Gaussian surface, named after Carl Gauss. Oh, I think he was German, but I don't remember. He was around the 1800s. He did a lot of stuff with math, astronomy, geophysics, optics, electrostatics, numbers theory, stats, and geometry. A lot of people did think about electric fields at the time, like the 1800s was a very hot time for electric fields. He's probably not the only person who came up with this treatment, but he did get to name the box, so there's something. So I have two questions about this box. Question number one, do you think it has to be a real box? No, it doesn't have to be real. This can be imaginary, right? I don't have to get out a cardboard box to look at electric fields, but I do need the idea of a box. Do we think it has to be a box? Does it have to be a cube? No, it doesn't have to be a cube either. It just has to be some surface that we can look at. So there's two big ideas.
Is the surface a conductive surface, or is it an insulated surface?
This surface, this is a nothing surface. So not conducting or insulating. It's just an imaginary surface. Yeah. It doesn't affect the electric field at all. Yeah.
And the surface could be anything symmetrical?
Symmetrical, that's a good word too. We do use it with symmetry because the symmetry lets us use this in a straightforward way. So Gauss's law applies to any situation. It's just that we can't solve the integrals with the hard situations, with the non-symmetric stuff, or I can't solve those integrals anyway. So here's a set of notes which I will release right after class. Our definition for a Gaussian surface is it's a closed surface through which an electric field can pass. Okay, so there's our definition of a Gaussian surface. It is an imaginary mathematical surface. It doesn't have to be physical. In general, when we do these problems, when we pick Gaussian surfaces, because we're going to see how we pick these, we always pick our Gaussian surface to look like our charge. So if we have a point charge or a sphere of charge, our Gaussian surface is going to be a sphere. If we had a line of charge, our Gaussian surface would be a cylinder. If we have a plane of charge, our Gaussian surface would be a box. Okay, so your surface should look like your charge so that we can take advantage of the symmetry. Okay, what else? The relationship between the arrows and the surface is really important. If the arrows point out, we know the charge is positive. If the arrows point in, we know the net charge is negative. We know that the number of lines is proportional to the size of the charge. So the next thing we're going to do is get a relationship that pulls all that stuff together. Okay, are we good to hear? Yep.
You know that it's proportional to the size of the charge. What's the ratio for charge to lines?
Is the next definition we're going to do, actually. Yeah. Okay, I'm just trying to let people get caught up on the notes before I go on to the next one.
Does the radius of charge increases with the amount of charge?
Just the rate, I'm not sure I totally understand your question.
Like, I'm just thinking, like, the electric lines are increasing with the amount of charge. So, is the radius of the charge also increasing along with the amount of charge?
Oh, I gotcha. When we talk about point charges, we say that those actually have no size. So whether it's 1Q or 3Q, it has exactly the same radius. But we will get into charges that have a finite size. We'll look at those for sure. Okay, so our next definition is what pulls those things together. We're going to talk about electric flux. Flux is a word maybe you know, maybe you don't know. Some people are familiar with that word. Flux in general, I just grabbed this out of the dictionary. It's a rate of transfer of fluid particles or energy across a given surface. So flux is a transfer, okay? So things moving. You can have a flux of water out of a pipe. Electric flux in particular, it's a scalar quantity. So the scalar bit is important. This is not a vector. This is just going to be a number. And it represents the number of electric field lines penetrating a surface. So electric flux is the bit that tells us about the number of electric field lines. The symbol for our electric flux is the Greek letter phi, and we put an E on it for electric field. It has units of newtons per coulomb times meters squared. So there's our symbol and our units. If we ask what electric flux depends on, we might have an idea that it depends on how big your electric field is. So if you have a bigger charge, you'll have a bigger electric field, you'll get more lines through a surface. It depends on the area of a surface. A small area will catch a few lines, a big area will catch more lines. And it also depends on the angle of the surface. So right here in this picture, and we'll do this in more detail on the next slide, you see that our surface is upright and our arrows are pointing through. But if we lay the surface flat, the arrows don't cut through, so the angle of the surface matters too. Okay, so these are things that the flux is going to depend on. So flux depends on the electric field strength E, the area of the surface A, and the tilt of the surface theta. It depends on all those things. So let's get an idea about that next. So this is just a set of arrows. Let's think about those arrows as being our electric field lines. So let's think about how the flux depends on all those things again. So I'm going to use my phone to be my surface we're talking about. So if I put my phone up here to be my surface, I see that I've got lines cutting through it. So the amount of flux, the number of lines, depends on the density of these lines. If I had twice as many lines, then more lines would cut through the surface. So that's why it depends on the electric field. It depends on the area of this surface. If I hold my phone this way, I have a whole whack of lines going through it. If I hold my phone this way, I don't have so many lines coming through here, so the area matters too. And then the last one, we're gonna build on this a good bit, is the angle of the surface. So this way, I have almost all the lines cutting through. This way, when it's at an angle, I have fewer lines cutting through. You're pretty good with that idea? So I want to talk about this for a little bit, that there are fewer lines cutting through. So I'm going to draw the area here. So this is the part on my phone. So this is the line that represents the area of my phone. I look at the lines cutting through it. I'm going to break this into two components. I'm going to get one part that's perpendicular to the field lines and one part that's parallel to the field lines. Okay, so this is my surface. This is the perpendicular bit. This is the parallel bit. The parallel bit, no lines cut through this one. The perpendicular bit, all of the lines cutting through the surface also cut through the perpendicular bit. So these two, the tilted surface and the perpendicular extension of the tilted surface, have the same number of lines. Everybody okay with that idea? Okay, so we need that concept to build to where we're going to get. I don't think I can do the next bit in like 3 minutes. So let's quit that here for right now. And then when we're back on Monday, we'll take this idea and we'll get our equation for electric flux.